Okay, so these are the three main effects of general relativity, or results of general relativity. Mass bends space, and that creates gravity. Mass bends time, and that slows time down. And gravity makes the wavelength of all light that comes away from the object longer. Okay, so let's apply everything that we've learned to the black hole situation. We want to know what happens to somebody if they were to fall into a black hole. And once we put all of this together, then we'll be done talking about this. So, here we go. Let's put it all together. Let me get a black hole on here. There we go. Okay, oops, let me zoom out a little bit. There we go. And let's say that way over here, I'll focus this in 1 second. Way over here, we got our spaceship. There we go. Focus, focus, focus. There we go. So we're set up just like in the movie Interstellar. The spaceship is far enough away from the black hole that it's not going to feel very strong effects from it. It's basically way off in space. But I finally take that guy we kidnapped. I take one of them, and I put him in a box. There we go. I put him in a box. And for the purposes of this this experiment, I've spray painted this box blue. It's a blue box. And right now, because he's closer to the black hole than us, he's going to feel a little bit more gravity than us. Okay, now, here we go. Let's call this the box point of view, and this the spaceship point of view, okay? Because what happens to this guy as he falls in is going to be different from different points of view. What the people in the spaceship see happen to the person in the box is going to be a little different than what he experiences from his point of view in the box. Because anything that was a result of relativity is relative. We're going to have different points of view on the effects of relativity here. Okay? Now, it looks like there's a question. Yeah. Sorry about our mad scientist character here. He is kind of a jerk. He's done with his test experiment, so he's kind of tossing it now. Check this out. Here we go. The first thing I want to talk about, though, is not an effect of relativity. So this effect is going to happen from everybody's point of view. Everybody's going to see this happen to the guy in the box. Okay, so first of all, he's going to fall towards the black hole. So as he gets closer and closer to the black hole, what happens to the amount of gravity he feels? As he gets closer to the black hole, what happens to the amount of gravity he feels? Is it more or less? More. Yes, it's more. It's more. And, okay. Let's call this the front of the box. I'll put a little F there for front. And let's call this the back. So, front of the box, back of the box. Which part of the box is going to feel the most gravity from the black hole? The front or the back? The front. And as he falls towards the black hole, the difference in what the front feels from the back will increase. So as he gets closer to the black hole, the front will feel more and more gravity than the back. And this situation should look familiar to you. We've seen this situation play out a lot in this course, What is that going to cause to happen? Oh, somebody even just guessed it before I even asked. Yes, this is going to cause the box to stretch, okay? As the box gets closer to the black hole, it's going to stretch out. And the closer he gets to the black hole, the more it will stretch. So this is a tidal effect. It's a tidal effect, but it's more extreme than any tidal effect we have seen. So if this box was just like a normal size box compared to his body right here, by the time he gets really close to the black hole, he could stretch over several miles. Now, can the human body survive this? Can the human body survive this extreme stretching? Here's a picture from your book that is kind of also explaining what would happen to him. As he goes towards the black hole, he would get more and more stretched out and thinner and thinner and thinner. This extreme gravity effect is bad for the human body because the human body is not very stretchy. So what would end up happening to his body and the box before they ever got to the black hole? What would happen to them? Yeah, you're going to die. You'll die from this tidal effect right here. Your body will be stretched out over potentially hundreds and hundreds of miles, and the human body is not stretchy, so you'll be ripped into bits. You'll just be ripped into a whole ton of bits. Kind of like a large rock getting ripped into little bits to become a ring. That's your body now. Yay! And what is this giant, strong tidal effect called? This extreme tidal effect around a black hole is called spaghettification. Yay! And that is an actual technical term for this. Spaghettification is the extreme tidal effect near a black hole. So if this person died from this, and there was an afterlife or something, if there was like a heaven or something, and he was in heaven and people were asking, hey, how did you die? And people were like, somebody murdered me. I fell down some stairs. This guy would be able to say, I died from spaghettification. Yes, based on the word spaghetti, yes. Spaghettification. There we go. Now, here we go. So, here's an important thing, though. Spaghettification has nothing to do with relativity. So, who sees it happen? If this is not a relativity thing, who sees it happen? Just the guy in the box? Just the spaceship? Or both? Who sees this happen to the guy in the box? Well, the box dude definitely sees it happen to himself. He's not going to be happy about this. It's not going to happen to the spaceship as long as it flies away, but they will see it happen to the guy in the box. So spaghettification happens to the box from everybody's point of view. It's not a relativity thing, okay? But everything else I'm about to mention is a relativity thing. So it's going to depend on your point of view. Okay, so number one, let's first talk about the space station's point of view. Okay, it's the space station's point of view. What do these people see happen to the box? Well, they see the spaghettification. We already said that. What's going to happen to the color of the box as it goes towards the black hole? What's going to happen to the color of the box? Yeah. It'll actually go through the whole rainbow in the red direction. It starts off blue, eventually it'll turn green, and then yellow, and then orange, and then red. And then after that, after red, what's going to happen? If it stretches that light, if it red shifts that light anymore, after the box turns red, what's going to happen? It'll go infrared, and then microwave, and then radio. So to the human eye, it would look like the box disappeared when the red shift happened too much. But we would still be able to track it all the way up to the event horizon if we had like a infrared telescope or a radio telescope. But we would have to look through those telescopes in order to see the box when it turned invisible, right? You wouldn't be able to see it with your own eyes. Okay, so there's going to be an extreme redshift. What's going to happen to time inside the box from the spaceship's point of view as the box gets closer and closer to the black hole? What's going to happen to time inside the box as it gets closer? It slows down. It slows down. And as they get closer and closer and closer, it goes more and more and more slow motion. And we would not be able to see it after it passed through the event horizon because no light can come out. But we can calculate what would happen to its time. As the gravity goes more and more and more towards infinity, how fast would time be moving at the actual singularity? If gravity goes to infinity there, how fast will time be moving right there? It would just stop. It would not be moving. It turns out the singularity itself does not experience time. Time does not move in a black hole. There is no time. So that would be another reason that it would be hard to figure out what a black, if you wanted to go visit one, if you somehow didn't die from the spaghettification, that's going to be freaky, right? Now check this out. Check this out, though. That means from our point of view, this box slowly turns into spaghetti. Its time slows down, and it gradually turns invisible. And then that spaghetti would just get slurped into the black hole and freeze in time. Frozen in time, literally forever. That's the spaceship's point of view. Okay? Now, what about the box's point of view? What about Box Guy? He does feel himself spaghettify and see himself spaghettify as he falls into the black hole. But yeah, that's a good one. Time will feel normal to him, okay? Time will feel normal to him. So he would not experience his time slowing down. But if he looked back at the spaceship, what would it seem like time was what was happening to time in the spaceship from this guy's point of view as he falls into the black hole? Remember, the spaceship has less and less gravity than him. So it would, yeah, time would look like it's speeding up out there in the spaceship. So that would mean as he falls more and more towards the black hole, the people in the spaceship would speed up more and more and more and more. And because of the gravity being so high at the black hole, when he gets really close to it, he might be able to see thousands of years go by out here. That's how fast time could be moving out here compared to his point of view. Would he be able to tell what was happening if things were going that fast? Probably not, because things would be just like a blur. But he would technically be able to see tons of time go by. That doesn't really help him, though, because he's going to fall into the black hole. Now, here's the next question. Would his box change color from his point of view? Would his box change color from his point of view? No. Because that's an effect of relativity. He's moving with the light source. The light source gets more and more stretched as it goes away from the object. But because he's at the light source, it hasn't had a chance to stretch much at all yet. So it's going to be blue. Just always remember, if it's on our general relativity list, it's different from different points of view. Cool. All right. So he falls into the event horizon. He falls into the event horizon. Technically, his pieces fall into the event horizon. He would still not be able to see the singularity. If he looks back out, if he's in the event horizon and somehow not dead, and somehow his brain was still working, would he be able to see out? Yes or no? Would he be able to see out of the event horizon? Yeah, so here's the thing. In the event horizon, you have to go faster than the speed of light to do what? In the event horizon, you have to go faster than the speed of light to do what? Leave or escape, right? Leave or escape. So if you're in the event horizon, let me zoom in here a little bit. You have to go faster than the speed of light to go this way, right? But if there's a person in here, if they're looking out, they are looking at light that comes this way. And there's no restriction on going that way. I'm zooming. Come on, focus. There we go. There's no restriction on going in. He was able to go in. Light's able to go in. It just can't leave. So if he goes in the event horizon, he won't even know he went in the event horizon because light is still coming in from outside. He would be able to see out, away from the black hole. If he turned around and tried to look at the black hole, he wouldn't be able to see that because light can't go this way. So basically, if you're falling into the black hole, it would look like the event horizon got smaller and smaller and smaller, but really you've already passed through it. You can see out, you just can't see in. And so he would be able to see our time go faster and faster and faster as he fell in, until he got slurped into the singularity and crushed infinitely forever and ever. Yay! So, let me put that all together. So, review. From the spaceship's point of view, what happens to somebody as they fall into a black hole is they get spaghettified. Their color red shifts until they become invisible to the human eye. It eventually becomes radio. And their time would go slower and slower and slower and slower, and then stop when they enter the black hole. That's the spaceship's point of view. From the box's point of view, from the point of view of somebody actually falling into the black hole, they are spaghettified, so that kills you. You're out of luck. That's not a relativity thing. But it won't be in slow motion. It'll be normal to you because your time is always normal to yourself. When you look back at the spaceship, you see their time speed up. And your spaceship stays the regular color all the way in. Or, sorry, your box stays the regular color all the way in. Okay. Okay. Don't visit a black hole. And spoilers, in Interstellar, at the end of the movie, the main character goes and enters into the black hole. All of that was BS, okay? All of that was BS. That's not going to happen that way. Because he didn't get spaghettified in the movie. The end of the Interstellar should have been his body ripping apart, and then all of his bits should have fallen into the black hole, and that would have been the end of the movie. But yeah, so parts of that movie are good, parts of the movie are bad. It should have been a bad ending. Now, somebody was asking about test questions. Just like the special relativity stuff, I'm going to ask very basic type of questions about this kind of thing on the test. So what I could ask is I could say, here's the situation. Here's the situation. If you're in the spaceship and you watch the box as it falls in, what will happen to the time in the box from the spaceship's point of view? And you would answer, if that was the question, you would say, the time in the box slows down. So as long as you remember these effects, I'm not going to ask I'm not going to give you like a crazy situation. It's just going to be a situation similar to this, and I'll ask about what the spaceship sees and what the box sees.